Hello, friend. Welcome back to another quiet journey through the cosmos. I'm so glad you're here tonight. Some nights when the world grows still and the mind begins to drift, a question arrives uninvited. Not loud, not urgent, just there, hovering in the space between waking and sleep. It's an old question. Ancient, really. One that philosophers whispered to the stars and scientists carved into equations. What holds everything together? What keeps the moon circling Earth, the Earth circling the sun spiraling through the galaxy? What invisible thread weaves through everything that exists, binding it all into something that makes sense? Tonight, we're going to follow that thread. Not to find answers. Answers are for daylight, but to drift alongside the mystery itself, the mystery of quantum gravity, the missing link of the cosmos. Before we begin our journey into the heart of this beautiful puzzle, if you find comfort in these quiet explorations, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. Imagine standing at the edge of a cliff, looking down into an endless canyon. On one side of this divide stands Albert Einstein, his hair wild with thought, his eyes fixed on the grand architecture of space-time. On the other side, a group of brilliant minds, Bohr, Heisenberg, Schrödinger, peers through microscopes into the strange, shimmering world of atoms. Between them, a gap. A silence. Two languages describing the same universe, yet somehow unable to speak to each other. Einstein gave us gravity reimagined, not as a force but as the gentle warping of space-time itself. Picture a trampoline. Place a bowling ball in the center, and the fabric dips, curves creates a well. Roll a marble nearby, and it spirals inward, following the curve. That's gravity, Einstein said in 1915. Mass bends space. Objects follow the curves. The sun doesn't pull the Earth. It creates a valley in space-time, and Earth simply falls along the slope endlessly in what we call an orbit. Elegant. Beautiful. Confirmed by every experiment, every observation, every eclipse that bent starlight exactly as Einstein predicted. Then came quantum mechanics. In the 1920s, scientists discovered something troubling. When you look closely at reality, I mean really closely down to the level of atoms and photons, the rules change completely. Particles don't have definite positions until you look at them. They exist in multiple states at once, probability clouds hovering in superposition. Light is both wave and particle. An electron passes through two slits simultaneously. Measure its position precisely, and its momentum becomes uncertain. Measure its momentum, and its position blurs into fog. Werner Heisenberg called this uncertainty. Not measurement error, not lack of precision. Fundamental uncertainty. The universe at its smallest scales refuses to be pinned down. Both theories work perfectly. Einstein's general relativity predicts the orbit of Mercury, the bending of starlight, the existence of black holes, the expansion of the universe. Quantum mechanics explains atoms, chemistry semiconductors, lasers, the entire technology of the modern world. Your smartphone works because quantum mechanics is true. GPS satellites work because Einstein's relativity is true. We live in a world where both are correct, yet they contradict each other. Not in the everyday world of falling apples and orbiting planets. There, the conflict sleeps. But push reality to its extremes, to the unimaginably small, the incomprehensibly dense, and the two theories begin to scream. At the heart of a black hole, where matter collapses to infinite density, Einstein's equations produce infinity. Mathematicians call this a singularity. A place where the math breaks, where prediction becomes impossible. At the birth of the universe, the Big Bang, the same problem. All of existence crushed into a point smaller than an atom. General relativity says here, space-time curves infinitely. Quantum mechanics says nothing can be that small and that certain. Both cannot be right. Yet both have never been wrong. Scientists call this the problem of quantum gravity. How do you describe gravity, the bending of space-time, using the language of quantum mechanics, where everything is probabilistic, where particles pop in and out of existence, where uncertainty reigns? It's like trying to write poetry using only mathematical symbols, or compose music using only colors. The tools don't match the task. Think about it for a moment. Have you ever tried to explain something you understood deeply to someone who spoke a different language? Not just different words, but different ways of thinking, different frameworks entirely. That's where physics has lived for nearly a century. Two perfect languages, one universe, no translator. Some thought the problem would dissolve with better experiments. It didn't. Others thought the math was simply incomplete. It wasn't. What became clear slowly through decades of brilliant work and beautiful failure is that we're missing something fundamental, some deep truth about reality that once understood will make both theories sing in harmony. That missing piece is quantum gravity, the theory that doesn't yet exist, the answer we're still searching for. But here's what makes this beautiful rather than frustrating. Every attempt to solve this problem has revealed something new, something unexpected. Each failed theory taught us that reality is stranger, more subtle, more magnificent than we imagined. String theory proposed that particles are tiny, vibrating strings, and suddenly we needed 10 dimensions. Loop quantum gravity suggested space itself is woven from quantum threads, and time became an illusion. Each idea opened doors we didn't know existed. Einstein himself never solved it. He spent the last 30 years of his life searching for a unified theory, trying to weave gravity and quantum mechanics into a single tapestry. He died in 1955 without finding it. Stephen Hawking devoted decades to understanding black holes through the lens of quantum mechanics. He discovered that black holes glow, that they evaporate, that information might be destroyed or might not be. He died in 2018 with the problem still unsolved. Yet their work wasn't wasted, far from it. They showed us where to look, what questions to ask, how deep the mystery really goes. Tonight we're going to walk through that mystery together. We'll visit the smallest possible places where space-time itself dissolves into quantum foam. We'll stand at the edge of black holes where gravity becomes so strong that even light cannot escape. We'll listen to the different stories scientists tell string theory's cosmic symphony loop, quantum gravity's woven space-time, and we'll see why each might be true or partly true or beautifully wrong in ways that point toward truth. You don't need to understand everything. Understanding is not the goal. The goal is to drift alongside wonder, to feel the edges of human knowledge, to rest in the comfort of mystery. Because here's the secret that nobody tells you. In science class, the most profound discoveries don't come from having answers. They come from asking better questions, from sitting with uncertainty, from being comfortable with not knowing. Every great physicist, every revolutionary thinker spent most of their time confused, gloriously productively confused. That confusion is not failure. It's the sound of a mind stretching towards something new. So, let's begin. Let's explore the two languages of reality, the smooth curved space-time of Einstein and the jittery, uncertain quantum realm, and discover why they need each other, even though they can't yet speak. The universe has been keeping this secret for 13.8 billion years. It can wait a little longer while we drift closer quietly to hear what it might whisper in the dark. Picture two orchestras playing simultaneously in the same concert hall. One plays Beethoven's structured, mathematical, predictable. Every note follows the one before with certainty. The other plays jazz improvised, probabilistic, alive with possibility. Each orchestra plays perfectly. Each creates beauty. But together, they create chaos. This is where physics found itself in the early 20th century, and where in many ways it remains. Let's step back to November 1915. Berlin. Albert Einstein, exhausted from years of calculation, finally completes his masterpiece, the field equations of general relativity. 10 elegant equations that describe how matter and energy curve the fabric of space-time. He had been chasing this for nearly a decade, driven by a simple observation. When you fall freely, you feel no gravity. Stand on Earth and you feel weight. Step off a building, don't actually do this. And for those terrible seconds, you float, weightless. Einstein realized this wasn't coincidence. Gravity isn't a force pulling you down. Gravity is the shape of space-time itself. Think of it like this. You're standing on a flat field, walking in a straight line. Easy. Now, imagine the ground beneath you begins to curve, to slope, to bend. You're still trying to walk straight, but the ground itself guides your path. You're not being pulled sideways. The very surface you're walking on is curved. That's what mass does to space-time. The sun, massive beyond comprehension, creates a deep well in the fabric of reality. Earth rolls along the edge of this well, trying to go straight, but the curved surface keeps it in orbit. No invisible ropes, no mystical forces reaching across empty space, just geometry, just shape. Within weeks, Einstein's equations explained something that had puzzled astronomers for decades. Mercury, the closest planet to the Sun, orbits just slightly wrong, according to Newton's gravity. Its orbit precesses shifts by 43 arc-seconds per century, a tiny discrepancy, but one Newton's laws couldn't explain. Scientists proposed hidden planets, unknown forces, mysterious clouds of dust. Einstein's curved space-time explained it perfectly instantly, with no additional assumptions. The Sun's gravity well is deeper than Newton imagined. Mercury skating along its edge feels that extra curvature. Then came May 29, 1919, a total solar eclipse. British astronomer Arthur Eddington traveled to the island of Principe off the coast of Africa. During totality, when the moon blocked the sun's glare, he photographed stars near the sun's edge. Einstein had predicted something extraordinary: the sun's mass should bend light itself. Starlight passing close to the sun should curve, making stars appear slightly displaced from their true positions. Newton's theory predicted a small shift. Einstein's predicted exactly twice as much. Eddington's photographs showed Einstein was right. Light, which has no mass, still follows the curves of space-time. Gravity doesn't pull light. Light simply travels straight through curved space, and straight in curved space looks curved to us. This wasn't just a successful prediction. It was a revelation. Space and time aren't fixed stages where physics happens. They're dynamic, flexible, woven together into a single fabric that bends and ripples and breathes with the matter it contains. Every massive object carries its own geometry. Black holes, predicted by Einstein's equations years before anyone believed in them, are places where this curvature becomes so extreme that space-time folds in on itself, creating a one-way membrane through reality. Gravitational waves, also predicted by Einstein, are ripples in space-time itself, the shiver of the universe when massive objects collide. For large-scale physics, planets, stars, galaxies, general relativity is flawless. Every test confirms it. Every observation agrees. The universe's expansion, discovered by Edwin Hubble in 1929, follows Einstein's equations. The cosmic microwave background, the afterglow of the Big Bang, matches relativity's predictions. GPS satellites orbiting Earth must account for Einstein's time dilation time, runs slightly faster in orbit than on Earth's surface, or they drift miles off course within days. Your phone knows where you are because Einstein was right about curved space-time. But let's travel to the other side of that canyon we mentioned. Let's descend into the quantum realm. In the 1920s, while Einstein was refining relativity, younger physicists were discovering something equally strange in a completely different domain. They were studying atoms' radiation, the behavior of light and electrons, and nothing made sense. Light sometimes acted like a wave, creating interference patterns spreading out through space, but other times light acted like a particle, a discrete packet of energy that could knock electrons loose from metal surfaces. This wasn't just confusing, it was contradictory. How could something be both wave and particle? Niels Bohr in Copenhagen, Werner Heisenberg in Munich, Erwin Schrödinger in Zurich. They developed quantum mechanics to explain this strangeness. Their answer was radical. Particles don't have definite properties until you measure them. An electron doesn't have a specific position and momentum simultaneously. It exists in a quantum state, a mathematical description of probabilities. Measure its position, and the quantum state collapses, crystallizing one possibility into reality. But before measurement, the electron is genuinely spread out, existing as potential, as probability, as cloud. Heisenberg formalized this in 1927 with his uncertainty principle. It's not about measurement precision. It's not about clumsy instruments disturbing delicate systems. It's fundamental. The more precisely you know a particle's position, the less precisely you can know its momentum and vice versa. Position and momentum are conjugate variables linked by quantum mechanics in such a way that perfect knowledge of both is impossible. The universe itself doesn't know. This isn't ignorance. It's how reality is constructed at the smallest scales. Schrödinger expressed this mathematically with his wave equation. Particles are described by wave functions, mathematical objects that evolve smoothly and predictably over time. But the wave function doesn't tell you where the particle is. It tells you the probability of finding it in various places if you look. The famous thought experiment Schrödinger's cat, poisoned or alive depending on a quantum event, wasn't meant to explain quantum mechanics. It was meant to show how absurd it seemed, that quantum uncertainty could influence the everyday world. Yet that absurdness is exactly how reality works. The double-slit experiment demonstrates this beautifully. Fire electrons one at a time through two narrow slits. Common sense says each electron goes through one slit or the other, but on the detection screen behind the slits, an interference pattern emerges, alternating bands of hits and gaps, exactly like waves overlapping and canceling. The only explanation: each electron somehow goes through both slits, simultaneously interfering with itself. Measure which slit it passes through and the interference vanishes. The electron observed chooses a path. The electron unobserved takes both. Einstein hated this. God does not play dice with the universe, he famously wrote to Max Born. He spent decades trying to prove quantum mechanics incomplete, that hidden variables must exist underneath, determining everything with clockwork precision. But experiment after experiment confirmed the quantum predictions. In the 1960s, physicist John Bell developed a theorem showing that no hidden variable theory could reproduce quantum mechanics results. Tests of Bell's inequality, especially Alain Aspect's experiments in the early 1980s, proved Einstein wrong. Quantum uncertainty is real. Have you ever felt torn between two certain truths that don't seem compatible? That's where physics lived. General relativity said, the universe is deterministic, smooth, continuous. Quantum mechanics said the universe is probabilistic, grainy, uncertain. Both were experimentally confirmed beyond any doubt. Both were mathematically rigorous and internally consistent. Yet they contradicted each other at the deepest level. In the everyday world, this conflict stays hidden. Why? Because gravity is breathtakingly weak. An electron orbiting an atomic nucleus feels electromagnetic forces, a trillion times stronger than gravity. Quantum effects matter immensely at atomic scales. Gravity barely registers. Conversely, for planets and stars, quantum uncertainty is negligible. Earth's position isn't uncertain by millimeters. It's a classical object following curved space-time. The two regimes don't overlap in ordinary experience, but push to extremes, and the piece shatters. Inside a black hole's event horizon, matter collapses toward infinite density. General relativity describes this collapse in exquisite mathematical detail until it reaches the singularity, a point of infinite curvature, infinite density, where the equations produce infinity and prediction stops. At the Big Bang, working backward through the universe's expansion, we reach a moment 13. 8 billion years ago, when all matter and energy occupied an infinitesimally small space. Again, infinities. Again, prediction fails. Quantum mechanics says, this is nonsense. Nothing can be infinitely small and infinitely certain. At Planck length about 10 to the power of negative 35 meters, unimaginably tiny quantum uncertainty becomes comparable to the scale of space-time itself. Below this scale, the very concepts of distance and duration lose meaning. Space-time, smooth and continuous in Einstein's vision, must become discrete, foamy, fluctuating. John Wheeler called this quantum foam a seething ocean of virtual particles and miniature black holes popping in and out of existence. Here, then, is the problem. General relativity requires a smooth, well-defined geometry of space-time. Quantum mechanics requires uncertainty fluctuations probability. Both can't be right in the same place at the same time. Yet both are our best descriptions of reality in their respective domains. One governs the cosmos, the other governs the atom. But at the Planck scale and black holes at the Big Bang, the two domains collide. This is why quantum gravity matters, not as an abstract puzzle, not as intellectual curiosity, but as the key to understanding the most extreme, most fundamental aspects of reality: the birth of the universe, the death of stars, the nature of space-time itself. Without quantum gravity, these remain mysteries wrapped in infinities, places where our best theories throw up their hands and say, "Here we cannot go." For nearly a century, physicists have searched for a bridge, a theory that speaks both languages fluently, a framework where space-time emerges from quantum laws, or where quantum mechanics emerges from space-time geometry. Something deeper than both, some fundamental truth from which Einstein's smooth curves and Heisenberg's uncertain clouds both arise. We haven't found it yet, but the search has been extraordinary. And as we drift deeper into this mystery, we'll see where that search has led to: vibrating strings in 11 dimensions, to space-time woven from quantum threads, to black holes that teach us about information and entropy. The journey into quantum gravity is a journey into the most beautiful failures and most stunning insights of human thought. But first, we need to understand just how small, how strange, how utterly alien reality becomes at the scales where this unification must happen. We need to visit the Planck scale itself, the ultimate frontier where space and time dissolve into something we have no words for yet. Imagine you could shrink yourself. Not just small, truly impossibly small, past cells, past molecules, past atoms. Through the nucleus, through quarks, beyond anything we've ever seen or measured. Keep going smaller and smaller until you reach a place where the very concept of size begins to lose meaning, where distance becomes uncertain, where time flickers like a candle in wind. This is the Planck scale, the bottom of reality. The place where our story must eventually lead. In 1899, a German physicist named Max Planck was studying black-body radiation, the light emitted by hot objects. He discovered something peculiar. Energy doesn't flow continuously. It comes in discrete packets, quantum chunks. From this insight, Planck derived a set of fundamental units, not arbitrary like inches or seconds, fundamental. Built from the most basic constants of nature, the speed of light, the gravitational constant, and Planck's own quantum constant. These units define the smallest meaningful measurements in the universe. The Planck length is roughly 1.6 times 10 to the negative 35 meters. The Planck time is about 5.4 times 10 to the negative 44 seconds. At these scales, physics as we know it dissolves into something else entirely. How small is the Planck length? Let's build some intuition. An atom is roughly 10 to the negative 10 meters across, already impossibly tiny. A proton nestled in the atom's nucleus is about 10 to the negative 15 meters, smaller still. But quarks, the particles that make up protons, have no measurable size. They appear point-like down to at least 10 to the negative 19 meters. The Planck length is 16 orders of magnitude smaller than that. If an atom were enlarged to the size of Earth, the Planck length would still be smaller than a human cell. But this isn't just about smallness. It's about what happens at that scale. According to quantum mechanics, uncertainty grows as you probe smaller distances. Heisenberg's uncertainty principle says that to measure something very precisely in space, you need very high energy. To probe the Planck length, you'd need energy concentrated so densely that it would collapse into a black hole. The very act of measuring destroys what you're trying to measure. This isn't a technological limitation. It's reality protecting itself from scrutiny. At the Planck scale, space-time itself becomes uncertain. Picture the smooth surface of a pond. From far away, it looks glassy, continuous, well-defined. Move closer, and you see ripples, small disturbances. Closer still, in a microscope, you'd see individual water molecules jostling chaotically. Space-time physicists suspect is similar. On large scales, human scales, planetary scales, it appears smooth, continuous, just as Einstein imagined. But zoom down to the Planck scale, and space-time becomes a seething foam of quantum fluctuations. Virtual particles pop into existence and vanish. Tiny black holes flash in and out of reality. The geometry of space writhes and twists on scales too small to observe. John Wheeler, Einstein's colleague and one of the 20th century's great physics poets, named this phenomenon quantum foam in the 1950s. He imagined space-time at the Planck scale as a froth of geometric activity, where the smooth fabric tears and reconnects, where wormholes might open and close in fractions of a Planck time. This isn't speculation without basis. It follows naturally from combining quantum uncertainty with gravitational energy. When you compress energy into a small enough region, gravity becomes strong enough to curve space-time severely. At Planck scales, this curvature becomes comparable to quantum fluctuations. The two can no longer be separated. Here's the problem Einstein's equations face. General relativity assumes space-time is a smooth continuum, differentiable, well-behaved mathematically. You can calculate curvature at each point because point has meaning. But in quantum foam, what's a point? If space-time itself fluctuates, if geometry is uncertain, then the very foundation of Einstein's theory crumbles. You can't solve equations that assume smoothness in a realm where smoothness doesn't exist. The math becomes ill-defined. Infinities appear. Predictions fail. Black holes reveal this crisis most starkly. When a massive star exhausts its nuclear fuel, gravity crushes its core. If the core exceeds about 3 solar masses, nothing can stop the collapse. Electrons are crushed into protons, forming neutrons. Neutrons themselves are compressed beyond stability. The core becomes a singularity, a point of infinite density, zero volume, infinite space-time curvature. At least that's what Einstein's equations predict. But infinite density is a warning sign in physics. It usually means your theory has reached its limit, that you're asking questions the theory can't answer. Quantum mechanics says this can't be right. Nothing can be infinitely dense and infinitely small. At some point, as the collapsing core approaches Planck, density about 10 to the power of 96 kilograms per cubic meter, an absurdly large number, quantum effects must become important. The singularity shouldn't form. Something else should happen. But what general relativity, our best theory of gravity, says, singularity. Quantum mechanics says no infinities allowed. Without a theory of quantum gravity, we simply don't know what happens inside a black hole's event horizon at the very center. The Big Bang presents the same puzzle but more urgently. Run the universe's expansion backward. Galaxies converge, space shrinks, temperature rises. About 13.8 billion years ago, all of space was compressed into a region smaller than an atom. Keep going back and you reach the Planck epoch, the first 10 to the negative 43 seconds after the Big Bang. Before this moment, the universe was so small, so dense, so energetic that quantum gravitational effects dominated everything. Space-time didn't just curve, it fluctuated quantum mechanically. Perhaps it didn't exist at all in the usual sense. Time itself might have been uncertain, fluctuating emergent from something deeper. What happened in the Planck epoch? We don't know. General relativity predicts a singularity, a moment of infinite density, infinite curvature, infinite temperature, the beginning of time. But again, infinity signals theoretical breakdown. Did time begin, or did it emerge from a timeless quantum state? Was there something before the Big Bang, a previous universe, a quantum bounce? Without quantum gravity, these questions have no answers. They're not just practically unanswerable, they're theoretically unanswerable. The math we have can't go there. This is what makes the Planck scale so crucial. It's not just where things get very small. It's where our two great theories, general relativity and quantum mechanics, must confront each other directly. No escape, no separation of regimes. At Planck, scale's gravity is quantum. Space-time is uncertain. The smooth and the probabilistic must merge, or our understanding fails. Think about the energy density at Planck scale. Take the Planck mass, about 22 micrograms, roughly the mass of a flea egg, and compress it into the Planck volume, a sphere with radius of 1 Planck length. The energy density is staggering, about 10 to the power of 113 joules per cubic meter. This isn't just hot, this is beyond hot. It's the energy density where space-time itself becomes a significant player in quantum dynamics, where the curvature of space affects quantum fields and quantum fluctuations affect space-time curvature, a feedback loop that our current theories can't handle. Physicists sometimes compare this to trying to use a ruler made of rubber to measure distances while standing on a trampoline. The ruler stretches as you use it. The trampoline bends under your weight. Neither provides a fixed reference. At Planck, scale's space is the rubber ruler, and time is the trampoline. Everything is dynamic, fluctuating, interdependent. There's no background stage, no fixed arena. Reality becomes self-referential in a way that breaks our usual mathematical tools. But here's what's beautiful. This isn't a failure, it's an invitation. Every time physics has encountered infinities or breakdowns, a deeper theory waited beyond. When Maxwell's equations predicted infinite energy in electromagnetic fields, quantum mechanics resolved it. When atoms should collapse according to classical physics, quantum mechanics explains stability. When starlight should be dragged by ether, relativity removed the ether. The infinities at Planck scale are telling us something profound. They're signposts pointing toward a theory we haven't discovered yet. Some researchers suggest that space and time might not be fundamental at all. Perhaps they're emergent, arising from something more basic, like how temperature emerges from molecular motion, or how fluidity emerges from countless water molecules, properties that don't exist at the smallest scale but appear when you zoom out. Maybe space-time emerges from quantum entanglement, from information from something we don't have words for yet. At the Planck scale, we might be seeing reality before it becomes space-time. Have you ever tried to imagine nothing, true, nothing, not empty space, but the absence of space itself? It's nearly impossible. Our brains evolved to navigate 3 dimensions. But at the Planck scale, those dimensions might dissolve into quantum superposition. North, south, forward, back. These directions might become uncertain, probabilistic, undefined, until something interacts, until a measurement happens. This leads to a fascinating possibility. What if the smoothness of space-time that we experience is like the smoothness of water? Water feels continuous, but it's made of discrete molecules. Could space-time be similar? Could it be composed of fundamental units, quantum pixels of reality, too small to detect individually, but creating the illusion of continuity when viewed from our scale? This idea animates one approach to quantum gravity, called loop quantum gravity, which we'll explore more deeply soon. space woven from quantum threads, geometry built from discrete connections. Another approach, string theory, suggests that at Planck scales particles aren't points, but tiny vibrating strings. The strings are roughly Planck length in size. Their vibrations create different particles, electrons, quarks, photons, even gravitons. Gravity becomes a quantum phenomenon because gravitons, the hypothetical particles carrying gravitational force, are just one vibration mode of these fundamental strings. At accessible energies, the strings look like points, but probe deep enough, and their extended structure becomes crucial: the common thread. Both approaches suggest that classical spacetime is an approximation, an excellent approximation at human scales, but an approximation nonetheless. Like Newtonian mechanics, is an approximation of relativity valid at low speeds, but breaking down near light speed. General relativity might be an approximation of quantum gravity valid at large scales, but breaking down at Planck scales. Here's the humbling part. We can't test this directly. We can't build a Planck-scale microscope. The Large Hadron Collider, humanity's most powerful particle accelerator, probes down to about 10 to the negative 19 meters. Impressive, but still 15 orders of magnitude larger than the Planck length. To reach Planck energy directly would require an accelerator the size of the Milky Way galaxy. We're not building that anytime soon. So, how do we make progress indirectly? By studying black holes where Planck-scale physics might leave observable signatures in Hawking radiation. By analyzing the cosmic microwave background where quantum fluctuations from the universe's first moments left patterns we can still detect. By using mathematical consistency, beauty, and logic to guide us toward theories that might be true even if we can't test them directly yet. By being clever. This is where quantum gravity research becomes as much philosophy as physics. What do we do when reality extends beyond our ability to measure? Do we trust mathematics alone? Do we demand experimental confirmation for every step? Different physicists answer differently, and that tension drives progress. String theorists often embrace mathematical elegance. Loop quantum gravity researchers often emphasize physical principles. Both are trying to peer into the Planck scale through different windows. One thing is certain. At the Planck scale, reality is stranger than anything we've encountered, stranger than relativity's curved space-time, stranger than quantum mechanics superposition. It's a realm where our most basic assumptions that space has 3 dimensions, that time flows forward, that events happen at definite locations, all become questionable. Not wrong exactly, but limited. True within their domain, but incomplete. As we continue deeper into quantum gravity, we'll meet the theories trying to describe this strange realm. Vibrating strings in hidden dimensions, space-time woven from quantum loops, black holes that teach us about entropy and information. Each approach offers a glimpse of what might lie at the foundation of reality. Each is incomplete, each is brilliant, and from their beautiful failures and partial successes, we're slowly learning what questions to ask, even if the answers remain elusive. What if everything, every particle, every force, every fundamental piece of reality is music, not metaphorically, literally? Tiny strings, impossibly small, vibrating in different patterns. Each pattern creates a different note in the cosmic symphony. An electron is one melody, a quark is another. Light itself is a rhythm. And gravity, that gentle curve of space-time we've been exploring, might be just another song sung by these invisible strings. This is string theory, perhaps the most ambitious, most controversial, most mathematically beautiful attempt to unify quantum mechanics and gravity. It emerged not from philosophy, but from a puzzle, a mathematical accident that turned into a revolution. And whether it's true or not, it's taught us more about the nature of reality than almost any idea in modern physics. Let's drift back to 1968. A young Italian physicist named Gabriele Veneziano was trying to understand the strong nuclear force, the force that holds quarks together, inside protons and neutrons. Experimental data showed strange patterns. Particles called mesons scattered in ways that existing theories couldn't quite explain. Veneziano, searching through mathematical functions, stumbled upon something called the Euler beta function. It fit the data beautifully, but nobody understood why. A few years later, physicists Leonard Susskind, Holger Nielsen, and Yoichiro Nambu realized something extraordinary. Veneziano's formula could be explained if fundamental particles weren't points, but tiny vibrating strings. One-dimensional objects like infinitesimally thin rubber bands oscillating in different modes. Each vibrational pattern corresponded to a different particle. The strong force wasn't fundamental, it was the interaction between strings. At first, this seemed like a clever mathematical trick, a way to organize messy data. But in 1974, John Schwartz and Joel Shirk discovered something unexpected in string theory's equations. Among all the possible vibration patterns, one had exactly the properties required for a graviton, the hypothetical quantum particle that carries gravitational force. Mass of 0, spin of 2, interacts universally with all energy. String theory didn't just describe particles, it predicted gravity, not added afterward, not forced in. Gravity emerged naturally from the mathematics unavoidable built into the structure. This was revolutionary. Every previous attempt to quantize gravity had failed because gravity and quantum mechanics seemed fundamentally incompatible. String theory bypassed the problem elegantly. If particles aren't points but extended objects, strings about 10 to the negative 35 meters long, roughly Planck length, then the mathematical infinities that plagued quantum gravity calculations simply vanish. Points can occupy the same location, creating infinite energy density. Strings can't. They're smeared out over a tiny region. That smearing smooths out the infinities. String theory was finite mathematically consistent and included gravity automatically. But there was a catch. Actually, several catches. The first became clear almost immediately. For the mathematics to work for the equations to be consistent, strings couldn't vibrate in just 3 dimensions of space. They needed more room. The original calculations required 26 dimensions. Later, more sophisticated versions incorporating supersymmetry, a symmetry between matter and force particles, brought this down to 10 dimensions. 10, not 3 plus time. 10 dimensions of space and 1 of time for a total of 11 in some formulations. Where are these extra dimensions? We don't see them. We move through 3 spatial dimensions, left, right, forward, backward, up, down. That's it. String theory's answer, proposed by Theodor Kaluza and Oscar Klein, decades before string theory existed, is that extra dimensions are compactified, curled up. Imagine walking along a tightrope. From far away, the rope looks one-dimensional, just length. Move closer and you see. The rope has thickness, a circular cross-section. Walk along the rope and you can move forward-backward along its length, but also around its circumference. The circumference is a curled dimension. String theory suggests 6 or 7 extra dimensions exist similarly curled up so small around Planck's scale that we can't perceive them directly. Different ways of curling up these extra dimensions create different physics in our 3-dimensional world. The shape of the hidden dimensions determines what particles exist, what forces operate, what constants of nature have, which values. Mathematicians study these shapes, complex geometric structures called Calabi-Yau manifolds, and researchers have found approximately 10 to the power of 500 possible configurations. That's not hyperbole. A 1 followed by 500 zeros. Each configuration potentially represents a different universe with different physical laws. Which one is ours? Nobody knows yet. This leads to one of string theory's biggest criticisms. With so many possible solutions, the theory seems to predict everything and nothing. It's incredibly flexible, perhaps too flexible. Physicist Peter Woit famously called it not even wrong, arguing that a theory that can accommodate any observation isn't making testable predictions. It's not science, it's mathematical philosophy. Others counter that this flexibility might be a feature, not a bug. Perhaps all those configurations are real, representing different regions of a vast multiverse. Our universe has the configuration it does because only certain configurations allow galaxies, stars, life to form. We exist in this one because it's capable of producing observers. But let's return to the strings themselves. Imagine them these tiny loops or segments of energy vibrating in empty space. Or rather, not an empty space itself might emerge from their interactions. A string vibrating in one pattern is an electron. Change the vibration and it becomes a photon. Another pattern produces a quark. The masses, charges, and other properties of particles aren't fundamental. They're vibrational modes, like how a violin string produces different notes depending on how it's played. The graviton appears as a closed string, a loop vibrating in a particular way. Its properties follow automatically from string theory's equations. This is stunning. In standard physics, we have to put gravity in by hand, constructing theories of quantum gravity that usually fail or produce infinities. In string theory, gravity is unavoidable. You can't have string theory without gravity. The universe, according to this view, is fundamentally gravitational because strings are fundamentally gravitational in their deepest vibrational state. But strings don't just vibrate, they interact. Two strings can merge into one string can split into two. These interactions, when calculated carefully, produce the same results as quantum field theory at low energies, the energies we can currently test. At high energies near Planck scale, string effects dominate and new phenomena emerge. The theory is incredibly rich, mathematically connecting to branches of pure mathematics that seem to have nothing to do with physics. Topology, number theory, algebraic geometry. String theorists have proven mathematical theorems that pure mathematicians couldn't crack using physics intuition. In the 1980s, string theory faced a crisis. There were 5 different consistent string theories, 5 separate frameworks, each with 10 dimensions, each slightly different, which was correct. It seemed arbitrary. Then, in 1995, Edward Witten proposed M-theory. Not a new theory exactly, but a recognition that all 5 string theories were different perspectives on a single deeper theory in 11 dimensions, like how a cylinder looks circular from one angle and rectangular from another. Same object, different views. M-theory united them. What the M stands for remains ambiguous. Membrane, mother, mystery. Perhaps all 3. M-theory introduced another object besides strings, baryons, short for membranes. These are higher dimensional surfaces. A 1 brane is a string. A 2 brane is a membrane like a soap bubble. 3 branes are volumes, and so on. Some researchers suggest our entire 3-dimensional universe might be a 3 brane floating in higher dimensional space. Gravity can propagate through all dimensions, but other forces are confined to our brain. That's why gravity appears so weak it's diluted across extra dimensions, while electromagnetism and other forces concentrate on our brain. This brain world scenario offers testable predictions. If true, we might detect gravitational effects from nearby branes. We might find evidence of extra dimensions in particle collisions or gravitational wave observations. So far, nothing. The Large Hadron Collider has searched for signs of extra dimensions, particularly microscopic black holes that might form if Planck energy is actually much lower in a higher dimensional space. No evidence yet. But absence of evidence isn't evidence of absence, especially when we're probing just barely beyond previously tested energies. String theory has also connected to black hole physics in profound ways. In the 1990s, Andrew Strominger and Kumrun Vafa used string theory to calculate the entropy of certain black holes, how much information they contain. The calculation matched Stephen Hawking's earlier results from semi-classical gravity exactly. not approximately, exactly. This was the first time anyone derived black hole entropy from a fundamental microscopic theory. It suggested string theory might truly understand quantum gravity, at least in some contexts. Yet the theory remains unproven experimentally. Some predictions seem testable in principal cosmic strings, relics from the early universe that might be detectable as gravitational wave sources, subtle deviations in the cosmic microwave background, supersymmetric particles that should exist if string theory is correct. But most predictions occur at Planck energy far beyond any foreseeable experiment. We're theorizing about scales 10 to the power of 16 times smaller than we can probe. Does this mean string theory is wrong? Not necessarily. Does it mean we should believe it? Not unconditionally. What it means is that we're doing physics at the frontier, where experiment and theory diverge, where mathematical beauty becomes a guide, because direct observation is impossible. History offers mixed lessons. Dirac predicted antimatter based purely on mathematical elegance, and it was real. But many beautiful theories have failed. Beauty correlates with truth, but doesn't guarantee it. String theorists often compare themselves to explorers mapping a vast continent. They've discovered mountains, rivers, cities of mathematical structure. But is it the continent where we live? Or is it an elaborate fictional geography, beautiful but disconnected from reality? Only nature can answer, and nature is being frustratingly quiet at the scales we need to check. What's undeniable is that string theory has deepened our understanding of quantum field theory, black holes, and mathematical physics. It's connected concepts that seemed unrelated. It's trained generations of physicists to think creatively about space-time and dimension. Even if string theory is ultimately wrong about our universe, it's almost certainly right about some universe. The mathematics is too consistent, too rich, too predictive to be pure fantasy. And perhaps that's enough for now. Perhaps quantum gravity is so difficult that even our wrong theories teach us essential lessons. Each failed attempt reveals another facet of the problem, narrows the space of possibilities, guides us toward truth, even through error. But string theory isn't the only path through this forest. Another approach takes a different starting point, entirely asking not what are particles made of, but what is space made of? That path leads to loop quantum gravity, where space-time itself becomes quantum woven from discrete threads that connect in a vast network of geometric relationships. What if space isn't smooth at all? What if when you zoom in far enough you discover that space itself has texture, structure, granularity, like fabric under a microscope revealing individual threads? Like a photograph dissolving into pixels? What if the emptiness between things isn't empty but woven a tapestry of quantum connections? Each thread, a relationship, each knot, a piece of geometry. This is the vision of loop quantum gravity. Not strings vibrating in space, but space itself made quantum. Space constructed from the bottom, up atom by atom, loop by loop. Where string theory asks what particles are made, of loop quantum gravity asks what space is made of. And the answer it offers is both strange and beautiful. Space is made of space, quantum space, discrete and relational, and fundamentally different from the smooth continuum Einstein imagined. The story begins differently than string theory's accidental discovery. Loop quantum gravity emerged from a deliberate program in the 1980s and 1990s, led primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin. Their goal was direct take Einstein's general relativity seriously as a description of geometry, then apply the mathematical machinery of quantum mechanics to space-time itself. No extra dimensions, no new particles, just quantum geometry. Quantize space the way physicists quantize the electromagnetic field to create photons. Make space-time granular, uncertain, probabilistic at the smallest scales. The technical breakthrough came from reformulating Einstein's equations in a new mathematical language. Instead of describing space-time curvature directly, Ashtekar expressed it in terms of loops closed paths through space. Imagine drawing curves in empty space connecting back to their starting points. These loops carry information about geometry, how space curves, how volume accumulates, how distances measure. In Ashtekar's formulation, these loops became the fundamental objects. Quantum states of geometry are built from networks of loops connecting and intersecting in intricate patterns. This network is called a spin network. The name comes from quantum mechanics, where spin describes intrinsic angular momentum. In loop quantum gravity, the edges of a spin network carry quantum numbers related to area and volume. The nodes where edges meet represent chunks of space. It's not space containing a network. The network is space. Remove the network and there's nothing left, not even emptiness, because emptiness requires space to be empty in. Here's where it gets fascinating. When you calculate the area of a surface using spin network, states you discover something remarkable. Area comes in discrete chunks. There's a minimum area related to Planck length squared about 10 to the negative 70 square meters. You can have this minimum area, or twice it, or 3 times it, but nothing in between. Area is quantized. Similarly, volume comes in discrete packets. Space isn't infinitely divisible. It has atomic structure, not metaphorically, literally. Space atoms. This immediately resolves some of general relativity's infinities. Black hole singularities happen when space gets crushed to infinite density and zero volume. But if volume can't be smaller than the Planck volume, singularities can't form. Something else must happen. Some researchers suggest Planck stars incredibly dense but finite objects that resist further collapse through quantum pressure. Others propose that space-time bounces, that collapsing matter reaches maximum density, and then rebounds, potentially creating a new expanding region, a universe on the other side of the black hole. The Big Bang singularity faces similar revision. Run the universe backward, and instead of reaching infinite density at time zero, you reach Planck density and stop. The equation suggests a bounce, perhaps our expanding universe emerged from a previous contracting phase, a cosmic breath inhaling and exhaling across eternal time. Loop quantum cosmology, a branch studying universe-scale implications, has developed detailed models of this. The quantum nature of geometry provides a natural repulsive force at extreme densities, preventing singularities while allowing evolution through what was previously a forbidden mathematical moment. But spin networks are static. They describe space at one instant. To incorporate time to describe how geometry evolves, loop quantum gravity uses spin foams. Imagine a spin network changing edges, reconnecting nodes, splitting or merging. The history of these changes traces out surfaces in space-time, two-dimensional structures representing how space evolves. A spin foam is a four-dimensional object, a space-time built from quantum geometry, where each surface represents a moment of spatial geometry and the whole foam represents history. Time in this picture isn't fundamental. It emerges from correlations between quantum geometric states. Carlo Rovelli has argued extensively that time is relational, not absolute. There's no universal clock ticking away in the background. What we call time is really change one part of the universe changing relative to another. At the deepest level, the universe doesn't evolve in time. It simply is a vast spin foam, a complete four-dimensional structure. Time appears when we slice through this structure, when we compare different regions, and notice correlations that create the illusion of flow. Does that sound strange? Consider this. You never experience time directly. You experience memory change causation. The sun rises after night. Eggs crack but don't uncrack. These asymmetries create temporal order. But fundamentally, the laws of physics, especially at quantum levels, don't distinguish past from future as strongly as our experience suggests. Entropy increases, creating an arrow of time, but entropy is statistical emergent from countless quantum events. Perhaps time itself is similar, emerging from quantum geometry rather than being fundamental. This is one of loop quantum gravity's most radical suggestions, and also one of its most philosophically challenging. We're deeply attached to time as fundamental. Our language structures past, present, future. Our consciousness seems to flow through time. But maybe that's just how geometric correlations feel from the inside. Maybe we're processes in a timeless spin foam, and the feeling of flow is our perception of internal relationships. Loop quantum gravity stays conservative in one important way. It doesn't require extra dimensions. Our 3 dimensions of space are enough. Quantum effects modify geometry, make it discrete, but don't demand hidden dimensions curled up beyond observation. This makes the theory philosophically lean. Occam's razor approved. Don't multiply entities beyond necessity. If you can explain quantum gravity with the dimensions we observe, why add more? But this conservatism creates challenges. Loop quantum gravity struggles to incorporate matter and force particles naturally. String theory gets particles from vibrations elegant unified. Loop quantum gravity treats matter separately, adding it to quantum geometry, rather than deriving it from geometry. The standard model of particle physics, electrons, quarks, photons, must be grafted onto the quantum geometric framework. Some researchers are working on unifying them, suggesting particles might emerge from topological features of spin networks, but this remains incomplete. Another challenge is dynamics. Spin networks describe spatial geometry beautifully. Spin foams describe space-time evolution. But deriving spin foam dynamics from first principles is extraordinarily difficult mathematically. Multiple proposals exist, each with different properties, different predictions. Researchers debate which formulation is correct, or whether all are approximations to something deeper. The mathematics is rich, but not fully understood yet. Loop quantum gravity also makes predictions, though indirect ones. The quantum nature of space might affect light traveling across cosmic distances. Different frequencies might experience slightly different geometries arriving at Earth, with tiny time delays after billion-year journeys. So far, gamma-ray burst observations have found no such effect, constraining but not eliminating the possibility. The theory also predicts modifications to Hawking radiation from black holes, potentially resolving information paradoxes we'll explore soon. One striking feature of loop quantum gravity is background independence. This technical term carries profound meaning. Most quantum theories assume space-time exists as a fixed stage where quantum events unfold. Loop quantum gravity doesn't. Space-time is quantum. There's no background geometry to build on. The geometry itself is uncertain, probabilistic, dynamically created by quantum states. This aligns deeply with Einstein's vision. Geometry isn't a container, but a participant in physics. Loop quantum gravity takes this seriously, perhaps more seriously than any other approach. Ravelli describes this as relationalism. Properties don't exist absolutely, but only in relationship. An electron doesn't have a position in absolute space. It has a position relative to other objects. Similarly, space-time doesn't exist absolutely, but only as a network of relationships between quantum geometric quanta. The universe is a web of interactions, not objects in a container. This philosophical stance, reminiscent of Leibniz, arguing against Newton's absolute space, animates loop quantum gravity's technical development. Critics argue that loop quantum gravity is too conservative, that it doesn't unify forces or explain particle physics, that it's quantum geometry without quantum matter. Proponents counter that modesty is wisdom, solve quantum gravity, first unification later. String theory tried to explain everything at once and got lost in mathematical possibilities. Loop quantum gravity focuses on one problem, making space-time quantum while preserving general relativity's core insights. There's also an aesthetic difference in communities. String theorists often work with high-energy particle physics, seeking unification and symmetry. Loop quantum gravity researchers often come from general relativity backgrounds, emphasizing geometric and conceptual clarity. The cultures value different things: mathematical richness versus physical principles, unification versus focus. Both are legitimate scientific values. Both drive progress. Have you ever noticed how the same problem can look completely different from different angles? How changing perspective reveals hidden structure. String theory and loop quantum gravity are different perspectives on quantum gravity. They use different mathematical languages, emphasize different principles, make different assumptions. Yet they might be describing the same underlying reality, the same deep truth about space-time at Planck scales, just using different words. Some researchers explore connections between the approaches. Can spin networks emerge from string states? Can string dualities relate to loop quantum gravity's background independence? These questions remain largely unanswered, but the possibility lingers. Perhaps there's a master theory beyond both, something that makes string theory and loop quantum gravity look like different approximations, or limits the way Newtonian gravity and special relativity are both limits of general relativity. What loop quantum gravity offers most powerfully is a different intuition about space, not as passive background, not as continuous medium, but as quantum active discrete relational. Space atoms connecting in vast networks, geometry built from quantum numbers, time emerging from correlations. It's a vision of reality where the stage itself is part of the play, where emptiness has structure, where nothing is woven from quantum relationships that create the illusion of smooth geometry when viewed from afar. And whether loop quantum gravity is ultimately correct or not, this vision changes how we think about existence. Space isn't nothing. It's something quantum, something built, something that can be studied, quantized, understood. That shift alone, from passive arena to dynamic participant, represents a profound advance in human understanding. These two approaches, string theory's vibrating entities and hidden dimensions, loop quantum gravity's woven space-time, in familiar dimensions, represent our deepest current attempts to touch quantum gravity. Neither is complete, neither is proven, but both are serious, beautiful, mathematically rigorous efforts to solve the hardest problem in theoretical physics. And there's one place where both approaches must ultimately succeed or fail, one phenomenon that serves as the ultimate testing ground for quantum gravity black holes, where space-time curves so extremely that quantum effects become unavoidable, where information and entropy dance at the edge of what's knowable. Imagine a place where gravity wins completely, where space-time curves so severely that it folds into itself, creating a boundary that nothing, not light, not matter, not information, can cross from the inside out. A one-way membrane in reality, a point of no return. Black holes are the universe's most extreme laboratories, places where Einstein's smooth geometry meets quantum uncertainty head-on, where theory must become precise or admit defeat. These cosmic enigmas aren't just objects, they're questions made physical, paradoxes wrapped in event horizons, and understanding them requires everything we've discussed: quantum mechanics, general relativity, the Planck scale, where both theories must finally reconcile. Black holes are where quantum gravity stops being abstract mathematics and becomes urgently necessary. The concept emerged early from Einstein's equations. In 1915, just months after Einstein published General Relativity, German physicist Karl Schwarzschild found an exact solution while serving in World War I. He was stationed on the Russian front, solving equations between artillery calculations. His solution described the geometry around a perfectly spherical, non-rotating mass. The math revealed something disturbing: a radius where the curvature becomes so extreme that escape velocity exceeds light speed. Inside this radius, called the Schwarzschild radius, or event horizon, nothing escapes. The mass itself collapses to infinite density at the center, the singularity. Einstein himself didn't believe black holes could actually exist in nature. They seemed like mathematical artifacts, pathologies of extreme idealization. Real stars rotate, have irregular shapes, undergo complex dynamics. Surely nature would avoid singularities. But Einstein was wrong. In the 1930s, Subrahmanyan Chandrasekhar showed that sufficiently massive stars must collapse after exhausting nuclear fuel. No known force could support them. J. Robert Oppenheimer and his student Hartland Snyder calculated in 1939 that this collapse would continue past any stopping point, creating exactly the objects Schwarzschild's math predicted. Still, nobody called them black holes yet. That name came from physicist John Wheeler in 1967, replacing earlier terms like frozen star or collapsed object. Wheeler understood that these weren't just dense objects, but fundamental features of space-time geometry. The event horizon isn't a physical surface. It's a mathematical boundary where the geometry tips where all future-directed paths point inward. Cross it, and you haven't hit anything. You've simply entered a region where every possible future leads to the center, to the singularity, where tidal forces stretch you infinitely thin in a process charmingly called spaghettification. For decades, black holes remained theoretical curiosities. Then, observations began. In 1971, astronomers detected X-rays from Cygnus X1, a system where a visible star orbits something invisible and massive, something pulling matter that heats to millions of degrees as it spirals inward. The orbital dynamics suggested the invisible object exceeded 3 solar masses too heavy to be a neutron star, a black hole candidate. By the 1990s, telescopes had found dozens more, stellar mass black holes from collapsed stars. Supermassive black holes at galaxy centers millions or billions of times the sun's mass. Then, in 2015, LIGO detected gravitational waves from 2 colliding black holes, each about 30 solar masses spiraling together and merging in a fraction of a second. The waves carried information about space-time itself, vibrating ripples from the most violent event in the universe, black holes colliding. 4 years later, the Event Horizon Telescope collaboration published the first image of a black hole's shadow, the supermassive black hole in galaxy M, 6.5 billion solar masses, showing the photon sphere where light orbits before either escaping or falling in. Black holes transitioned from theory to observed reality. But observing black holes from outside doesn't tell us what happens at the center or at quantum scales. For that, we need theoretical physics. And here's where things become wonderfully strange. In 1974, Stephen Hawking calculated something nobody expected. Black holes aren't perfectly black. They glow, very faintly but definitely. They emit thermal radiation through a quantum process now called Hawking radiation. Here's how it works. Quantum field theory says empty space isn't truly empty. It's seized with virtual particle-antiparticle pairs popping into existence and annihilating almost instantly. This happens everywhere constantly, a consequence of quantum uncertainty. Near a black hole's event horizon, something remarkable can occur. A pair forms just outside the horizon. One particle falls in. The other escapes. To an outside observer, it looks like the black hole emitted a particle. The energy for this comes from the black hole's mass via Einstein's mass-energy equivalence. The black hole loses energy. It evaporates. The process is excruciatingly slow for large black holes. A solar mass black hole has a temperature of about 60 billionths of a degree above absolute zero, colder than the cosmic microwave background. It absorbs more radiation than it emits, but as it shrinks, it heats up. A black hole half as massive is twice as hot, radiating faster. Eventually, in the far future long after stars have died, black holes will evaporate completely, ending in a flash of high-energy radiation. Even the most massive black holes will vanish, given enough time. Trillions upon trillions of years, but finite. Hawking radiation revealed something profound. Black holes have temperature, and anything with temperature has entropy, a measure of disorder, of information content, of the number of microscopic states corresponding to a macroscopic configuration. Jacob Bekenstein, then a graduate student, had already suggested this in 1972. He argued that black holes must have entropy proportional to their surface area, not volume. Hawking's calculation confirmed it. The Bekenstein-Hawking entropy formula states that a black hole's entropy equals its event horizon area, divided by 4 times the Planck area. This is strange. Usually entropy scales with volume. A box of gas has entropy proportional to how many molecules fit inside. But black holes are different. All their entropy lives on the surface. This led to the holographic principle proposed by Gerard T. Hooft and refined by Leonard Susskind. The idea is radical. All the information contained in a 3-dimensional region of space can be encoded on its 2-dimensional boundary. The universe might be fundamentally 2-dimensional, with 3-dimensional physics emerging as a hologram, a projection from the boundary. String theory embraced this idea. In 1997, Juan Maldacena discovered the ADS/CFT correspondence, a precise mathematical relationship between a 5-dimensional spacetime with gravity and a 4-dimensional quantum field theory, without gravity living on its boundary. Gravity in the bulk corresponds exactly to quantum phenomena on the surface. This remains one of the deepest insights in theoretical physics, suggesting that quantum gravity and quantum mechanics might be different descriptions of the same reality related by holography. But Hawking radiation created a crisis called the black hole information paradox. Quantum mechanics insists that information is never truly lost. If you burn a book, the information isn't destroyed. It's scrambled into smoke and radiation, theoretically recoverable if you could track every particle. But Hawking radiation seems thermal random, carrying no information about what fell into the black hole. A black hole could swallow an encyclopedia and a pile of random matter with the same mass. Both would evaporate identically, producing indistinguishable radiation. Where did the information go? 3 possibilities emerged. First, information is destroyed, violating quantum mechanics. Second, information remains inside an ever-shrinking black hole, preserved in a Planck scale remnant after evaporation. Third, information somehow escapes encoded in subtle correlations in the radiation that Hawking's semi-classical calculation missed. For decades, physicists debated. Hawking initially argued for information destruction. Leonard Susskind insisted on preservation, leading to a famous bet that Hawking eventually conceded in 2004, though the mechanism remained unclear. Recent work suggests information does escape, but through quantum entanglement between radiation particles emitted at different times. The black hole's interior becomes entangled with the exterior in ways that preserve information while appearing random to simple measurements. Page-Kerb's calculations by Don Page showing how entropy should evolve suggest information begins escaping around the halfway point of evaporation. String theory and loop quantum gravity both offer mechanisms for this, though details differ. Then came the firewall paradox in 2012. Physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and Joam Sully, collectively, AMPS, discovered a conflict. Preserving information through entanglement requires that late radiation is entangled with early radiation. But quantum mechanics says particles can only be maximally entangled with one other system. If late radiation is entangled with early radiation, it can't be entangled with particles inside the black hole. Yet general relativity requires smooth geometry at the horizon, which demands entanglement between inside and outside. Something must give. The proposed solution, a firewall, a wall of high-energy particles at the event horizon that destroys anything crossing it. This contradicts Einstein's equivalence principle, which says, freely falling observers shouldn't notice anything special at the horizon. You should pass through smoothly, like stepping from air into water, only realizing you've crossed after the fact. but a firewall would incinerate you instantly, which is correct. The paradox remains unresolved, though ideas proliferate. Maybe the event horizon is fuzzy quantum smeared rather than sharp. Maybe black holes have internal structure we don't understand. Maybe entanglement and space-time geometry are more deeply related than we thought. One radical proposal is ER equals EPR, suggested by Juan Maldacena and Leonard Susskind in 2013. ER refers to Einstein-Rosen-Bridges wormholes shortcuts through space-time. EPR refers to Einstein-Podolsky-Rosen pairs quantum entangled particles. The proposal, they're the same thing. Entangled particles are connected by microscopic wormholes. Quantum entanglement is geometric, a tiny tunnel through space-time linking separated regions. If true space-time geometry emerges from quantum entanglement, space itself is woven from quantum connections, a notion that resonates with loop quantum gravity's vision while using string theory language. Black holes also offer potential experimental windows into quantum gravity. Primordial black holes, if they exist, are tiny black holes formed in the early universe's extreme conditions. Those with masses around 10 to the power of 15 grams would be evaporating now, producing detectable gamma rays. Searches continue. None found yet, but absence doesn't rule them out. Detecting Hawking radiation from any black hole would be extraordinary, confirming quantum gravitational predictions. Gravitational wave observations from merging black holes also probe extreme gravity. When black holes spiral together, space-time around them oscillates wildly. LIGO and Virgo detectors measure these waves testing general relativity in strong field regimes. So far, Einstein's predictions hold perfectly, but future detectors might be sensitive enough to detect quantum corrections, tiny deviations from classical predictions that reveal quantum gravity's influence. Think about what black holes represent. Their boundaries, limits, places where reality becomes extreme enough that our theories must be complete or fail. Singularities tell us our math is insufficient. Event horizons create paradoxes about information. Hawking radiation connects quantum mechanics and gravity unavoidably. Every black hole is a laboratory we can't enter, but can study from outside, learning about physics at scales we can't directly probe. What would it feel like to fall into a black hole? From your perspective, nothing unusual happens at the horizon. You cross it still alive, still intact, noticing no boundary. But as you continue inward, tidal forces grow. Gravity at your feet exceeds gravity at your head. You stretch. The difference increases exponentially. Long before reaching the singularity, if there is one, you're torn apart, atom by atom. But your experience of time also dilates. As you fall, you might see the entire future history of the universe flash before you. Starlight blue shifted to gamma rays, the cosmos aging and dying as you descend toward the center. To an outside observer, something different happens. They watch you approach the horizon, redshifting and slowing. Time dilation becomes extreme. You appear to freeze approaching the horizon asymptotically, but never quite crossing your image, fading to invisibility as photons redshift infinitely. The outside universe sees you preserved forever on the horizon, information never quite entering. Both perspectives are valid, yours and the external observers, describing different slices through the same space-time geometry. Black holes taught us that gravity and thermodynamics connect deeply. That information is fundamental, that space-time might be emergent from quantum entanglement, that the universe's most extreme objects are also its most revealing places where nature shows us directly what our theories must accomplish. And as we search for quantum gravity through strings, through loops, through new ideas, yet undiscovered black holes will remain the testing ground, the place where theory meets reality at its most unforgiving. But quantum gravity isn't only about theory. It's also about observation, about finding ways to detect signatures of Planck-scale physics in the observable universe. And that search takes us to some of the most ambitious experiments humans have ever conceived, listening for whispers, from the quantum foam searching for gravitons hiding in the noise of the cosmos. Imagine trying to catch a whisper in a thunderstorm, a single photon of light in the glare of the sun, a ripple in a pond during an earthquake. That's what detecting quantum gravity signatures feels like, searching for the faintest possible effects in a universe filled with overwhelming noise. Yet scientists persist, building detectors more sensitive than anything previously imagined, listening for messages from the Planck scale, hoping to catch reality at its most fundamental, revealing itself through the slightest tremor. The search begins with a particle that may not exist as we imagine it. The graviton, the hypothetical quantum carrier of gravitational force. Just as photons carry electromagnetic force and gluons carry the strong nuclear force, gravitons would carry gravity mediating gravitational attraction between masses through quantum exchange. Every theory of quantum gravity predicts gravitons in some form. String theory identifies them as a particular vibration mode. Loop quantum gravity describes them as excitations of quantum geometry. But detecting a single graviton, that might be impossible, not because of technology, but because of physics itself. Freeman Dyson calculated in 2013 that detecting an individual graviton would require a detector so massive it would collapse into a black hole before completing a measurement. Gravity is astoundingly weak compared to other forces. The electromagnetic force between two electrons is about 10 to the power of 43 times stronger than their gravitational attraction. That's not a typo. Gravity is 43 orders of magnitude weaker. A refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. This weakness makes gravitons nearly impossible to detect individually. They interact so feebly that they pass through ordinary matter, as if it weren't there. But weakness creates opportunity. While individual gravitons evade detection, gravitational waves, coherent collections of countless gravitons, if gravitons exist, can be measured. In September 2015, LIGO detected gravitational waves from two black holes merging 1.3 billion light-years away. The signal was a chirp lasting a fraction of a second, stretching and compressing space by less than 1/10,000th the diameter of a proton, smaller than an atomic nucleus. Yet, LIGO measured it. The detectors themselves are marvels. Each consists of two 4-kilometer-long arms arranged in an L shape. Laser light bounces between mirrors at the ends. When a gravitational wave passes, it stretches one arm while compressing the other. The interference pattern of returning laser beams shifts minutely, revealing spacetime's vibration. The sensitivity is absurd. LIGO can detect a change in arm length smaller than the diameter of a proton across 4 kilometers. That's like measuring the distance to the nearest star to within the width of a human hair. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of black hole mergers and neutron-star collisions. Each event sends ripples through space-time, carrying information about extreme gravity. So far, all observations match general relativity's predictions perfectly. No deviations, no anomalies. Einstein's century-old equations describe merging black holes with exquisite accuracy. But could quantum corrections hide in the data? Could subtle modifications to gravity at small scales leave traces in gravitational waveforms? Researchers search for such signatures. Quantum gravity might produce echoes, reflections of gravitational waves bouncing off quantum structure near event horizons. Some analyses claim to see hints of echoes in LIGO data. Others find the evidence inconclusive. The debate continues, constrained by detector sensitivity and statistical significance. Future gravitational wave detectors, space-based observatories like LISA, planned for the 2030s, will be more sensitive, probing lower frequencies where supermassive black holes merge, potentially revealing quantum gravitational effects more clearly. Another search focuses on quantum entanglement in curved space-time. Entanglement is pure quantum mechanics. Two particles sharing a quantum state such that measuring one instantly affects the other regardless of distance. Einstein called this spooky action at a distance and never fully accepted it. But experiments confirm it repeatedly. Quantum mechanics is non-local in this precise sense. Now, researchers ask, how does gravity affect entanglement? Does curved space-time modify entangled correlations in detectable ways? Experiments are underway. In 2017, China's Maisha satellite demonstrated quantum entanglement between photons separated by over 1,000 kilometers using Earth's curvature to test how gravity's pull affects quantum correlations. Results so far show no deviations from standard quantum mechanics. But these are gentle tests. Stronger gravitational fields near neutron stars or black holes might reveal effects we can't yet detect. The goal is to put quantum mechanics and gravity in the same experiment, forcing them to interact, seeing if standard theories suffice or if modifications emerge. Tabletop experiments offer another approach. Instead of cosmic scale observations, create quantum superpositions of massive objects in laboratories. In 2019, researchers in Vienna demonstrated quantum interference with molecules containing thousands of atoms. Future experiments aim higher, microdiamonds, metal spheres, perhaps even millimeter-scale objects placed in quantum superposition. If successful, these would be macroscopic objects visible to the naked eye, existing in two places simultaneously. Why does this matter for quantum gravity? Because massive objects carry gravitational fields. Place an object in superposition, and its gravitational field superposes too. Does space-time itself enter superposition? Or does gravity somehow resist quantum behavior, remaining classical while the object becomes quantum? Different theories predict different outcomes. Measuring gravitational interactions between quantum superposed masses might reveal quantum gravity effects at accessible scales, bypassing the need for Planck energy accelerators. Proposals include macroscopic quantum resonators, which would levitate microspheres in space, isolating them from environmental interference, then measure gravitational interactions while the spheres exist in quantum superposition. QGEM. Quantum gravity-induced entanglement of masses proposes using two masses whose only interaction is gravitational. If they become entangled through gravity alone, that proves gravity is quantum. If not, something profound is missing from our understanding. These experiments face extraordinary technical challenges. Quantum superposition is fragile. Any interaction with environment, stray photons, air molecules, vibrations destroys it. Larger masses are harder to isolate. Gravitational forces are weak, requiring exquisite sensitivity. But technology advances. What seemed impossible decades ago becomes routine. Quantum computers manipulate superpositions of billions of states. Atomic clocks measure time to 18 decimal places. Perhaps quantum gravity experiments currently at the edge of feasibility will soon become practical. Cosmic rays offer accidental experiments. These high-energy particles from space occasionally reach energies near the Planck scale, not quite there, but closer than any accelerator achieves. When ultra-high-energy cosmic rays hit Earth's atmosphere, they create particle showers studied by observatories like the Pierre Auger Observatory in Argentina. If quantum gravity modifies physics at extreme energies, cosmic ray behavior might show anomalies. Slight violations of Lorentz invariance, the principle that physics looks the same in all inertial reference frames, could indicate Planck scale structure. Observations so far find nothing unusual. Cosmic rays behave as standard physics predicts. But this constrains quantum gravity theories. Some models predicted observable Lorentz violations. Their absence rules out certain approaches or pushes Planck scale effects to even higher energies. Negative results are still results, narrowing possibilities guiding theorists toward models consistent with observation. Photons traveling across cosmic distances offer another test. If space-time has quantum structure, discrete granular foam-like photons of different energies might experience slightly different geometries. Light would disperse like sunlight through a prism, but far more subtly. After traveling billions of light years, different colors might arrive at slightly different times. Gamma-ray bursts, explosive events visible across the universe, provide ideal tests. They emit photons of vastly different energies within milliseconds. If quantum gravity affects propagation, photons should arrive at Earth with measurable time delays proportional to energy. In 2009, NASA's Fermi Gamma Ray Space Telescope observed a burst from 7.3 billion light-years away. High-energy and low-energy photons arrived within milliseconds, setting tight constraints on quantum gravity effects. Some theories predicted delays large enough to detect. The observations ruled them out. Once again, reality proved more subtle than hoped. But constraints matter. Each null result eliminates possibilities, focuses effort, refines models. There's an irony here. Quantum gravity might be true, but undetectable directly. Planck scale effects might be so suppressed at accessible energies that no conceivable experiment reveals them. We'd be in the position of early atomists correct about atoms, but unable to see them relying on indirect evidence and theoretical consistency. Some physicists find this acceptable. Others demand experimental confirmation, arguing that untestable theories aren't science. This tension shapes the field. String theorists often embrace mathematical beauty and internal consistency as guides when experiments can't reach relevant scales. Loop quantum gravity researchers emphasize physical principles and conceptual clarity. Both approaches have merit. History shows that theories later confirmed were often developed through mathematical reasoning before experiments validated them. Maxwell's equations predicted electromagnetic waves decades before Hertz detected them. Dirac's equation predicted antimatter years before Anderson observed positrons. Sometimes math leads and reality follows, but history also warns against overconfidence. Many beautiful theories prove wrong. Many elegant mathematical structures describe nothing real. Without experimental feedback, how do we distinguish physics from philosophy? This question haunts quantum gravity research. Are we doing science or sophisticated speculation? The answer might be both, and that's acceptable in a transitional period where theory far outpaces experiment. Have you ever worked on a puzzle missing half its pieces? You can infer the missing parts from patterns from the shapes of neighboring pieces, from the picture gradually emerging. That's quantum gravity research. We have pieces from general relativity, pieces from quantum mechanics, pieces from black hole thermodynamics. We're inferring what's missing, building theories from partial information, hoping that when we finally see the complete picture, perhaps through an unexpected observation or breakthrough experiment, our guesses will prove at least partially correct. The search also extends to more speculative territory. Wormhole shortcuts through space-time might exist at quantum scales, popping in and out of existence in space-time foam. If microscopic wormholes are common, they might leave signatures in particle physics. Virtual particles traveling through wormholes could create subtle non-local correlations. So far, none observed. But the search continues. Quantum gravity might also affect the early universe in observable ways. Inflation, the rapid expansion in the universe's first fraction of a second, stretched quantum fluctuations to cosmic sizes, creating the seeds of galaxies. Quantum gravity corrections during inflation might leave distinctive patterns in the cosmic microwave background, the relic radiation filling space. Current observations show no such patterns, but future telescopes with greater sensitivity might detect them. The universe itself becomes a laboratory, its early moments preserving fossil evidence of Planck-scale physics. Some researchers explore the idea that quantum gravity eliminates the Big Bang singularity, replacing it with a quantum bounce where the universe contracts to Planck density then rebounds. Such bounces might produce observable signals, gravitational waves with specific frequencies or patterns in matter distribution. Loop quantum cosmology predicts these signatures. Observations haven't confirmed them yet, but neither have they been ruled out. The search continues across multiple wavelengths and observation types. There's something beautiful about this search. Humans bound to one planet orbiting an ordinary star, peering across billions of light years, and down to Planck scales, trying to understand reality's deepest structure. We can't travel to black hole horizons. We can't shrink to Planck length. But we can think, calculate, observe, infer. We can build detectors sensitive enough to measure space-time quivering. We can launch satellites to watch the cosmos carefully. We can use nature's extreme events, supernovae, cosmic rays, merging black holes, as experiments we could never perform ourselves. And whether we detect quantum gravity signatures or not, the search teaches us. It pushes technology to new limits. It forces precision in the theory. It reminds us that the universe operates at scales far beyond human experience, yet remains comprehensible to human minds, willing to think carefully and look closely. That's perhaps the most hopeful lesson. Reality is knowable even when it's incredibly difficult to access. But quantum gravity isn't only about fundamental physics. It's also about what changes if we solve it. What new understanding emerges, what implications flow from unifying gravity and quantum mechanics. And those implications ripple outward from physics into philosophy, into our understanding of time, space, and existence itself. What if time didn't begin? What if the Big Bang wasn't the start, but a transition, a moment of transformation in an eternal cycle? What if every black hole contains an entire universe branching infinitely, and we live inside one such cosmic seed? These aren't science fiction fantasies. They're serious proposals emerging from quantum gravity research ideas that fundamentally rewrite our understanding of existence, causation, and reality's deepest nature. Solving quantum gravity wouldn't just fill a gap in physics, it would transform everything. Our conception of before and after, the meaning of space and emptiness, whether the universe is unique or one bubble in an infinite foam, whether time flows or simply is. These aren't distant philosophical questions. They're immediate consequences of understanding how space-time behaves when gravity becomes quantum. Let's begin with the most direct implication: what happens before the Big Bang. Standard cosmology says the universe began 13.8 billion years ago in a hot, dense state and has been expanding ever since. Run the expansion backward and everything converges to a singularity, infinite density, infinite temperature, infinite curvature. General relativity says this singularity is real, a boundary of space-time, where physics stops, where the question, what came before, is meaningless because time itself begins there. But quantum gravity changes this story. We've seen how loop quantum gravity suggests space has a minimum volume, preventing infinite compression. When cosmologists apply these ideas to the universe's birth, a field called loop quantum cosmology, pioneered by Martin Bojewald, and other singularities disappear. The universe compresses to Planck density about 10 to the power of 96 kilograms per cubic meter, then rebounds. Quantum gravitational repulsion emerging from space-time's discrete structure prevents further collapse and drives expansion. Our Big Bang might be a big bounce, the transition from a previous contracting phase to our current expanding phase. This opens extraordinary possibilities. Perhaps the universe is cyclic, eternally bouncing between expansion and contraction. Each bounce creates new physics, new constants, perhaps even new dimensions of space. We live in one cycle among infinitely many. Before our Big Bang was another universe contracting and compressing until quantum effects triggered rebound. Before that, another cycle, and another. Time extends infinitely into past and future, with big bounces marking transitions rather than beginnings. Observational tests for this exist. A bouncing universe might leave imprints in the cosmic microwave background, subtle patterns in temperature fluctuations, reflecting quantum gravitational dynamics during the bounce. So far, observations show no clear signatures, but sensitivity improves. Future telescopes might detect whispers from the pre-bounce universe encoded in light that's traveled 13.8 billion years to reach us. Another implication involves black holes and baby universes. Lee Smolin proposed cosmological natural selection in the 1990s, a provocative idea connecting black holes to universe creation. The hypothesis when a black hole forms quantum gravitational effects at the singularity don't just prevent infinite collapse. They create a new expanding region of space-time disconnected from our universe. A baby universe born from black hole collapse with its own big bang, its own space and time. We couldn't see these baby universes. They'd be causally disconnected beyond any event horizon, unreachable by light or information. But if true, the implications are staggering. Every black hole, and there are billions in our galaxy alone, spawns a new universe. Those universes contain black holes that spawn more universes. Reality becomes an infinite tree branching endlessly. Our universe isn't special or unique. It's one node in a vast cosmic genealogy descended from a black hole in some parent universe, giving birth through its own black holes to countless offspring universes. Smolin added an evolutionary twist. Baby universes inherit physical constants from their parents with slight mutations from quantum fluctuations during formation. Universes with constants that efficiently produce black holes have more offspring. Over countless generations, the multiverse evolves toward universes optimized for black hole production. Our universe, with its particular values of gravitational, constant electron mass, speed of light, might reflect this selection pressure. We exist because our constants allow stars, which produce heavy elements, and eventually black holes, maximizing reproductive fitness in this cosmic evolutionary landscape. Critics note, this remains speculative, lacking direct evidence. We can observe baby universes or test the hypothesis experimentally, but it demonstrates how quantum gravity enables entirely new cosmological frameworks, ways of thinking about existence that go beyond anything general relativity or quantum mechanics alone suggests. Quantum gravity also transforms our understanding of time's nature. We experience time as flowing, carrying us from past through present toward future. This seems fundamental, undeniable. Yet relativity showed time is relative flowing at different rates depending on motion and gravity. Quantum mechanics introduced time evolution of wave functions, but neither theory explains why time flows, why we remember past but not future, why causes precede effects. Some quantum gravity approaches, particularly Julian Barber's work, suggest time might not be fundamental at all. In his timeless interpretation, the universe is a vast space of possible configurations every arrangement matter and geometry could have. What we call time is really just correlation between different parts of this configuration space. We perceive flow because brain states that remember certain configurations are correlated with configurations we call later. But fundamentally, all configurations exist timelessly. The universe doesn't evolve. It simply is a four-dimensional block, and our consciousness traces paths through it, creating the illusion of flow. This connects to loop quantum gravity's suggestion that time emerges from quantum geometry, rather than being built into spacetime's foundation. At Planck scales, perhaps there's no meaningful time, ordering no before or after. Time crystallizes only when quantum geometry correlates in ways that create causation and sequence. This isn't just philosophical speculation. It changes how we formulate quantum gravitational theories. What boundary conditions make sense? What questions are meaningful? Another radical implication comes from Eric Verlinde's entropic gravity proposed in 2010. Verlinde suggested gravity isn't fundamental, but emergent. arising from statistical mechanics and quantum entanglement in a manner similar to how temperature emerges from molecular motion. In his framework, space-time itself is emergent, appearing from underlying quantum information. Gravity is the entropic force pushing systems toward configurations with higher entropy. And the geometric picture Einstein gave us is effective, not fundamental. If true, this reframes quantum gravity entirely. We shouldn't quantize gravity because gravity isn't fundamental. Instead, we should understand how classical space-time emerges from quantum entanglement in information. The project becomes explaining gravity from first principles rather than forcing gravity into quantum formalism. Verlande's ideas remain controversial and incomplete, but they illustrate how quantum gravity thinking can invert entire approaches. Questioning assumptions we thought secure, quantum gravity also intersects with the multiverse. String theory's vast landscape of possible vacuum states, 10 to the power of 500 configurations, might all be real, representing different regions of a megaverse where different physics operates. Eternal inflation, a cosmological model where space perpetually expands and creates new bubble universes, gains support from some quantum gravitational calculations. Our observable universe becomes one bubble among infinite others, each with different constants, different dimensions, different laws. This raises anthropic questions. Why do we observe the particular constants we do? Perhaps because only certain combinations allow complex structures, stars, planets, life. We necessarily find ourselves in a universe capable of producing observers. The alternative that our constants are unique and specially chosen seems increasingly untenable. Quantum gravity, by providing mechanisms for multiple universes or multiple vacuum states, makes anthropic reasoning scientifically respectable rather than philosophically desperate. Consider practical implications too. Understanding quantum gravity might enable technologies we can barely imagine. When Maxwell unified electricity and magnetism in the 1860s, he couldn't foresee radio, television, smartphones, the internet, all consequences of electromagnetic theory. Similarly, a complete theory of quantum gravity might enable manipulation of space-time itself. Not tomorrow, not next century, but eventually. Imagine technologies that create microscopic wormholes for communication, devices that manipulate quantum geometry for computation, methods of extracting energy from vacuum fluctuations or space-time curvature. These sound like fantasy, but so did nuclear energy before we understood atomic physics. More immediately, quantum gravity might resolve the dark energy mystery. Observations show the universe's expansion is accelerating, driven by something filling space with negative pressure. Einstein's cosmological constant fits observations, but requires incredibly fine-tuning. Its value is about 10 to the power of 120 times smaller than quantum field theory predicts. Why? Perhaps quantum gravitational effects naturally produce this small value. Perhaps dark energy isn't constant, but a dynamic field related to quantum geometry. Solving quantum gravity might simultaneously explain cosmic acceleration. Quantum gravity also affects our understanding of determinism and free will, not by answering these philosophical questions, but by changing their terms. If time is emergent, if the universe is a timeless configuration in space, if reality is fundamentally quantum and probabilistic, then classical notions of cause and effect require revision. This doesn't prove or disprove free will, but it suggests the debate needs reformulation using quantum gravitational insights about time's nature and causation structure. There's a lesson here about how science progresses. Often solving one problem reveals that the question was framed incorrectly. Before relativity, people asked about absolute time. Afterward, the question became meaningless. Before quantum mechanics, people assumed complete determinism. Afterward, fundamental randomness became essential. Similarly, quantum gravity might reveal that questions like what caused the Big Bang or what happens at singularities were badly posed, arising from inappropriate application of classical or semi-classical thinking to regimes where it doesn't apply. Have you ever solved a puzzle only to realize the picture was different than you expected? That's where physics is with quantum gravity. We thought we were completing a picture of space-time and particles. Instead, we're discovering that space-time might be emergent. Particles might be vibrations or geometric excitations. Time might not be fundamental, and reality's structure is far stranger than Newton-Einstein or even Bohr imagined. This strangeness isn't failure, it's progress. Each generation of physics has found reality stranger than the previous generation thought. Classical mechanics gave way to relativity and quantum mechanics, both deeply counterintuitive. Quantum gravity promises to be stranger, still challenging our notions of space-time and causation in ways we're only beginning to grasp. But through this strangeness, we're learning what the universe actually is not what we wish it to be, or what our intuition suggests. One implication feels especially poignant. Quantum gravity reveals how little we know and how much remains mysterious. We understand perhaps 5% of the universe's content, ordinary matter and radiation. Dark matter and dark energy constitute the rest, and we don't know what they are. We understand physics at accessible energies, but not at Planck scale. We can describe the universe's evolution from fractions of a second after the Big Bang, but not before. We're conscious beings in a quantum universe, and we have no idea how consciousness relates to physics. Quantum gravity won't answer everything, but it might reshape enough that entirely new questions become askable, and perhaps that's the real implication. Not specific predictions about bouncing universes or baby cosmoses, but a fundamental openness to radical revision of our most basic concepts. If solving quantum gravity requires that time is emergent, or space is discrete, or dimensions are fungible, or reality is holographic, then so be it. Nature decides. Our job is to listen carefully, calculate precisely, observe attentively, and adjust our concepts to match reality rather than forcing reality into comfortable conceptual boxes. As we drift toward this journey's end, one question remains. What does all this mean? Not just technically, but humanly. What does it tell us about existence, about knowledge, about our place in this strange and beautiful cosmos? Part 9. Closure. The beautiful incompleteness. So here we are at the end of our journey through the deepest mystery in physics. We've traveled from Einstein's curved space-time to Heisenberg's uncertain quantum realm. We've descended to the Planck scale, where reality dissolves into foam. We've listened to strings singing in 11 dimensions and watched space-time weave itself from quantum threads. We've stood at black hole horizons where information dances on the edge of knowability. We've searched for gravitons in the cosmic silence and reimagined the universe's birth as a bounce rather than a beginning. And yet, the question remains unanswered. Quantum gravity, the missing link of the cosmos, still eludes us. Not because physicists aren't brilliant enough, not because the mathematics is too hard, but because nature guards its deepest secrets, carefully revealing them, only to those patient enough to ask the right questions, humble enough to accept being wrong, and brave enough to keep searching when the path disappears into uncertainty. There's something profound in this incompleteness, something beautiful. Think about what we've learned not by solving the problem, but by trying. String theory taught us that dimensions might be more flexible than we imagined, that particles and forces might be different notes in a cosmic symphony. Loop quantum gravity showed us that space itself might be woven discrete, emergent, rather than fundamental. Black hole thermodynamics revealed connections between gravity, quantum mechanics, and information that nobody expected. The holographic principle suggested our three-dimensional reality might be a projection from two-dimensional boundaries. These insights didn't come from finding the answer. They came from the search itself, from beautiful failures and partial successes, from theories that explain some things brilliantly while leaving others mysterious. This is how science actually works, not as a steady march toward truth, but as a dance with mystery, where each step reveals new questions more interesting than the ones we started with. Einstein spent the last 30 years of his life searching for a unified theory. 30 years. He never found it. When he died in 1955, his notebooks were filled with equations that didn't quite work, ideas that almost converged but never fully aligned. Some people see this as tragedy. Einstein, the greatest physicist of his generation, dying with his final quest unfulfilled. But maybe that's the wrong way to see it. Maybe Einstein's search, even unfinished, taught us more than his success would have. He showed us that unification was possible in principle, that electricity and magnetism, seemingly different forces, were really aspects of one electromagnetic field. That space and time, apparently separate, were really unified space-time. That mass and energy, distinct in Newtonian physics, were interconvertible through that most famous equation. If these unifications were possible, why not others? Why not gravity and quantum mechanics? Einstein's failure gave permission to everyone who came after to dream big, to attempt the impossible, to believe that nature's deepest structure might be elegant and unified, even if we haven't found that unity yet. Stephen Hawking faced a similar incompleteness. He discovered that black holes radiate, connecting gravity to thermodynamics and quantum mechanics in unexpected ways. He spent decades wrestling with the information paradox, whether information is preserved when black holes evaporate. He proposed solutions refined, then changed his mind. The famous bet with Leonard Susskind, conceded in 2004, wasn't admission of failure. It was acknowledgement that the problem was deeper than initially thought, that simple answers weren't sufficient, that mystery remained. Hawking died in 2018. The information paradox isn't fully solved. Recent progress suggests information does escape encoded in quantum correlations, too subtle for Hawking's original calculation to capture. But the final answer, still uncertain. Multiple approaches, string, theory loop, quantum gravity, holography, offer different perspectives, different partial solutions. None complete, none universally accepted. Yet, Hawking's work wasn't wasted. His questions shaped an entire field. His paradoxes forced physicists to think more carefully about quantum mechanics, information theory, and the nature of space-time. Do you see the pattern? The giants of physics, Newton, Maxwell, Einstein, Bohr, Heisenberg, Hawking, they solved enormous problems. But they also left enormous mysteries. Newton explained planetary motion, but couldn't explain gravity itself. Maxwell unified electromagnetism, but introduced the ether, which doesn't exist. Einstein gave us relativity, but rejected quantum mechanics implications. Heisenberg revealed uncertainty, but struggled with quantum field theory's infinities. Each generation solves some puzzles and creates new ones. This isn't failure. This is how knowledge grows. Not as completion, but as deepening. Not as reaching final answers, but as discovering better questions. Quantum gravity feels incomplete because it is incomplete. And that incompleteness is the most exciting thing about it. It means the story isn't over. The universe still has secrets to reveal. The next generation of physicists will discover things we can't yet imagine, using tools and concepts we haven't invented. Think about the practical implications we've discussed. When Maxwell unified electricity and magnetism in the 1860s, it was pure theory, beautiful mathematics, elegant equations. Nobody imagined radio, television, computers, smartphones, the entire information age. Maxwell's equations made modern civilization possible, but Maxwell died in 1879 without seeing any of it. The technology came decades later, built by people who understood what Maxwell's mathematics actually meant. Similarly, quantum mechanics in the 1920s seemed like abstract physics relevant only for understanding atoms. Now, it's the foundation of chemistry, materials, science, semiconductors, lasers, medical imaging, quantum computing. The entire modern economy rests on quantum mechanical principles that Heisenberg and Schrödinger worked out with pencil and paper nearly a century ago. What will quantum gravity enable? We don't know, we can't know. But if history teaches anything, it's that fundamental physics has practical consequences, often decades or centuries later, in ways nobody predicted. Understanding space-time at the quantum level might lead to technologies we literally can't imagine now. Not because they're impossible to describe, but because we lack the conceptual framework to even think about them. Perhaps manipulating quantum geometry could enable new forms of computation. Perhaps understanding how space-time emerges from quantum entanglement could revolutionize communication or information storage. Perhaps resolving the cosmological constant problem, explaining dark energy through quantum gravitational effects, could reveal new energy sources or propulsion methods. These sound like science fiction. So did space travel before we understood orbital mechanics. So did nuclear power before we understood atomic structure. So did the internet before we understood electromagnetism and quantum mechanics. But the practical applications, however exciting, aren't the main point. The main point is understanding. Humans want to know. We're curious. We look at the night sky and ask why. We dig into the earth and ask how. We peer through microscopes and telescopes and ask what. This curiosity isn't optional or frivolous. It's fundamental to being human. It's what makes us different from other animals. We don't just survive, we wonder. Quantum gravity is the ultimate expression of this curiosity. It asks, what is space? What is time? What happened at the universe's beginning? What happens at a black hole's center? These aren't practical questions. They won't cure diseases or feed the hungry or solve immediate problems. But they're important anyway, because we're not just bodies that need feeding. We're minds that need wondering. And here's the beautiful part. Everyone who works on quantum gravity knows it might not be solved in their lifetime. String theorists understand that experimental confirmation might be decades or centuries away. Loop quantum gravity researchers know their approach might be incomplete or wrong. Everyone working on these problems accepts tremendous uncertainty. They're not guaranteed success. They're not even guaranteed progress. They might spend entire careers pursuing ideas that turn out to be dead ends. Yet they continue. Why? Because the question matters. Because the search itself is meaningful. Because being part of humanity's attempt to understand reality at its deepest level is worth doing even if you personally don't reach the answer. This is profound. It's almost spiritual. Scientists working on problems they might never solve, contributing pieces to puzzles that might take centuries to complete. Trusting that future generations will build on their work, learn from their mistakes, and eventually maybe find truth. Have you ever started a project knowing you might not finish it? Planted a tree knowing you might not see it fully grown? Contributed to something larger than yourself, trusting others will carry it forward? That's what quantum gravity research feels like. Collective, transgenerational, an act of faith in human curiosity and persistence. There's a lesson here beyond physics. Life itself is incomplete. We're born into stories already underway. We'll die before those stories end. The questions we care most about, why are we here? What does it mean? What happens after don't have definitive answers we can prove. Yet we live anyway. We love, create, explore, wonder. We contribute what we can to the ongoing human story, knowing we're one chapter in something much longer. Quantum gravity research embodies this. It's humanity asking the deepest possible questions about physical reality, knowing the answers might take centuries pursuing truth anyway, because truth matters. It's accepting that we're small, tiny conscious specks in an unimaginably vast cosmos, while simultaneously being grand, because those tiny specks can think, can understand, can touch infinity with mathematics and imagination. As we close this journey, consider what it means that we can even ask these questions. 4 billion years ago, Earth had no life. 3 billion years ago, single-celled organisms floated in oceans. 500 million years ago, the first animals appeared. 60 million years ago, our mammalian ancestors were small creatures hiding from dinosaurs. 2 million years ago, our hominid ancestors learned to make tools. 10,000 years ago, we invented agriculture. 400 years ago, we invented science. 50 years ago, we learned quantum mechanics and general relativity were incompatible and started seriously trying to unify them. In the universe's 8 billion year history, the last 50 years, this moment, our moment, is the first time matter has organized itself into structures capable of understanding quantum gravity as a problem. The universe, through us, is trying to understand itself. Stars lived and died to create the atoms in your body. Galaxies collided to shape the space you inhabit. The Big Bang itself set conditions allowing your existence. And now, using the consciousness that evolution built from stardust, you listening to this, can grasp ideas about quantum foam, string theory, loop, quantum gravity, concepts that describe reality at scales far beyond human experience. That's staggering. That's beautiful. That's enough reason to care about quantum gravity, even if we never solve it. Because the fact that we can ask the question, can follow the mathematics, can peek at reality's deepest structure, that alone is miraculous. The incompleteness isn't frustrating, it's an invitation. To young people who might become physicists, the problem is unsolved. You could be the one who makes the breakthrough. To everyone else, the universe is stranger, more wonderful, more mysterious than we imagined. Even knowing what we don't know is knowledge precious and hard-won. Quantum gravity reminds us that reality is weirder than common sense suggests. Space and time aren't the rigid stage they appear to be. They're dynamic, quantum, possibly emergent. Particles aren't tiny billiard balls, but excitations of fields, or vibrations of strings, or geometric defects in quantum space-time. The universe doesn't owe us intuitive answers. It is what it is regardless of what we find comfortable or comprehensible. And yet, here's the miracle: it's comprehensible. Difficult, yes. Counterintuitive, absolutely. But comprehensible. Humans can understand quantum mechanics and general relativity. We can calculate with Planck units and Calabi-Yau manifolds. We can design experiments sensitive enough to detect space-time vibrations. We can think clearly about things we can never directly experience. The universe is vast and strange, but it follows rules. Mathematics describes those rules, and human minds somehow can grasp that mathematics. This suggests something profound about the relationship between mind and cosmos. We're not separate from the universe looking in. We're part of the universe looking at itself. The same laws that govern stars and atoms also govern neurons and thoughts. When physicists understand quantum gravity, not if, because eventually it won't be humans conquering nature. It'll be nature understanding itself through human consciousness. So, we return to where we began the question. What holds everything together? What thread connects the quantum and the cosmic? We've explored answers, strings, loops, holography, emergent space-time. Each brilliant, each incomplete. The true answer remains hidden, but closer than it was a century ago. Each generation brings us nearer. Each failure teaches. Each partial success illuminates. And in the meantime, we have the privilege of living in an age when quantum gravity is an active research area. When brilliant minds worldwide work on the problem. When experiments probe relevant regimes. When mathematics connects previously disparate ideas. We're witnessing the search in real time. Future historians will look back at this era as the moment when humanity began seriously grasping how space-time and quantum mechanics unite. We're living through that. How extraordinary is that? Thank you for joining me on this journey through the deepest mystery in physics. Thank you for your patience with difficult ideas, your willingness to sit with uncertainty, your openness to wonder. The universe is vast and strange and beautiful. Quantum gravity is our attempt to touch its deepest essence. We haven't succeeded yet, but we're trying. And the trying itself is magnificent. Maybe tonight as you drift towards sleep, you'll think about space-time fabric beneath you curving gently under Earth's mass, or quantum fluctuations in empty space constantly creating and destroying virtual particles. Or strings vibrating in dimensions you can't see, or loops of quantum geometry weaving reality itself. Not to understand completely, that's not necessary, just to feel the wonder of it, the mystery, the incompleteness that makes the story worth continuing. We've walked through neurons and dreams, through light and silence, through Planck scales and cosmic horizons. We've touched the edge of human knowledge and found it thrilling, humbling, inspiring. Knowledge was never meant to be completed, only felt pursued, celebrated as an ongoing conversation between curious minds and mysterious reality. The story continues. New physicists are training now, learning the mathematics, preparing to ask questions we haven't thought of yet. New experiments are being designed. New theoretical frameworks are emerging. Quantum gravity will be solved maybe in decades, maybe in centuries. But it will be solved because humans don't give up on questions that matter. And when it's solved, new mysteries will emerge. Deeper questions will appear. That's how it works. That's how it should work. The universe doesn't end with quantum gravity. It extends infinitely beyond, always offering new puzzles, new wonders, new invitations to understand. Until we meet again for another quiet journey through science and mystery, take care of yourself. Keep wondering, keep questioning, keep looking up at the night sky with curiosity and joy. The cosmos is vast, but you're part of it, made of stardust, shaped by evolution, conscious and curious. That's enough. That's everything. Sleep well, friend. Dream gently. And when you wake, remember the universe is stranger and more beautiful than we know, and the search to understand it continues. Good night.